Okay, so I'm Luke, and today I will tell you how we can find meteor energy from acoustic data. So using infrasound, which is sound below human hearing, below about 20 hertz, we can hear meteors when they fall. So a meteor entry will emit shock waves in sort of like a line source, and a fragmentation along this trajectory will generate shock waves in a spherical source, out like these pictures show here. And so these shock waves will transition from a strong shock into a weak shock, and then into an acoustic wave rather quickly from the meteor. And so these acoustic waves will travel through our atmosphere, being pushed around by winds and affected by the temperature gradients. And they will either hit a seismic or infrasound station on the ground, or they will fall near one, and they will cause the ground to shake near the station and also be detected. In addition, we could have an impact shown down here, and which would also be detectable, but those are so rare that we're not going to consider those here. And so there's a few key advantages of infrasound. You can detect at any brightness. You can detect during the day, during the night, during the full moon. And so if it acts as an independent method, so if you miss a meteor optically, then you might be able to fill in the gaps with infrasound data. The data is already being taken for other purposes, because we have so many seismograms around the world looking for earthquakes. The data already exists, and the detectors are already in place, and so we can just take all of the data that is being accumulated. And so here's a map of all of the currently operational stations in the world, which we can easily take data from for observing meteors infrasonically. And so what can we find? Similar to the earthquake problem of finding the epicenter, we can find the supercenter of a fragmentation. That is, instead of our epicenter being below the ground, now we have a supercenter above the ground, and the acoustic waves travel through our atmospheres instead of through the Earth. And so if the meteor falls within about 150 kilometers of a few stations, we can begin analysis on it, and we can actually we can triangulate the fragmentation in that way. Similarly, you can do the same with a trajectory. However, this time you need a few more constraints with more stations, because instead of solving for a point source, now you're solving for a line source. And so both of these have been done in the past before successfully. In addition, you can find the total energy of the trajectory by using the period of the waveform at an infrasound station, and you can actually estimate the total amount of energy deposited by the trajectory. However, this assumes that the body stays intact the entire flight. It assumes single body, and so some of the energy might be missing due to a fragmentation. And so we need a way to estimate the energy of a fragmentation along the trajectory. And so that's what this research aims to accomplish. So we used the Stubenberg meteor as an example. We've chosen this one because it fell within about 100 kilometers of an infrasound station, IS-26. And so we used this one. It had multiple fragmentations, and so here is a trajectory, just basically a quick idea of what's happening, and it fragmented about 4 or 5 times, and the acoustic waves were heard at an infrasound station. And so here's the actual waveform that arrived at our infrasound station. And so we've noted 5 specific events on the waveform with different overpressures. And so we need to explain all of these 5 points. And so we have the timings of when they arrive, and we also know the trajectory very well from optical data from SPERNI. And so we can use this to find the height of each fragmentation if these are fragmentation points. And so this is our ray tracing algorithm. If we have a given fragmentation occurring at a specific position and height and time, and we have a given station, we can ray trace how the acoustic wave travels through our atmosphere, being pushed around by winds and temperature gradients. And so a fragmentation occurs at a specific time, and then it takes an additional amount of time for the sound to get to a station. However, we want to also estimate the uncertainty of our atmosphere during this travel time. And so we've used a Monte Carlo perturbation scheme with the given spread of the atmosphere, the given variability of the atmosphere. And we've run this multiple times for each ray tracing solution, and we get a slightly different acoustic path, and therefore a slightly different arrival time. And so we can use this to estimate our uncertainty in the acoustic travel time. And so up here, I've shown, this is the sample waveform, and then I've used a sample fragmentation along the trajectory at about 32 kilometers in height. And so this dark pink line here shows the expected arrival of the acoustic waves from the fragmentation given the nominal atmosphere. And these dashed pink lines around it represent the arrivals in the perturbed atmospheres. And so we get sort of a few seconds of uncertainty due to the atmospheric uncertainty. And so this shows our uncertainty in the arrival time of a given fragmentation. And so we can do this many times to estimate where or what height the fragmentations came from. So what we did is we took many fragmentations along the trajectory, sample fragmentations, between 17 and 50 kilometers, and we used many perturbations as well. And so we tried to find which ones would be closest to, which ones have times closest to the timings that we saw on the waveform. And so these 5 fragmentations, these 5 features here, are shown as the pink lines on this graph in timing here. And we found that arrivals at these heights up here align the best within perturbations with these ones here. And so we've given about a 3 seconds or 1 kilometer in distance tolerance for these values. And we found that these features here have heights as shown here, with our range in height demonstrating what our atmospheric uncertainty is. So we know that we can relate energy and overpressure measured at an infrasound station by blast scaling. It goes to about the power of 1/3. However, the overpressure measured at the station is different from the overpressure at the fragmentation. We have to account for the fact that the overpressure of the acoustic wave will actually attenuate as it travels through the different pressure levels of our atmosphere. And so there's frequency attenuation in which it'll shrink the amplitude. And there's also geometric attenuation, where the acoustic waves will interact with each other, either spreading apart or going together. And so taking those into account, we come out with this plot here. So all of these lines represent an energy versus overpressure, and we see the trend of to the power of 1/3 shown here. However,
2 minutes.
Yep, thank you. They're slightly offset from each other, and this is because they each have their own attenuation conditions. So fragmentation 1 occurs at about 21 kilometers in height, while fragmentation 5 occurs at about 32 kilometers in height. And so they have to go through different amounts of atmosphere and therefore are attenuated differently. And so that's why we see this offset here. So showing the energy released versus height, we can see that the relative heights between the fragmentations of each other is consistent with the light curve provided with Spurney. And so like the highest fragmentations seem to be the most dominant, as well as that's also seen in the light curve as well. It's in the heights as well. These straight lines represent the peaks here, and so they align well with the heights as well. It is unclear whether these 2 fragmentations are actually possibly the same fragmentation, or if they are 2 distinct fragmentations. It's unclear from the infrasound data so far. So to conclude, we present a method to estimate energy from acoustic data, and the analysis tool which we have used to do all of this energy analysis and position analysis, bolide acoustic modeling, or BAM, will be available on GitHub. Thank you.
Thank you. perfect timing, 8 more seconds. So this is excellent. And also the content was very interesting. Any question? What? Go away, please. Not you, but the noise. So, anyone with raised hand? I cannot see anyone. Tom, oh, there are already. Go ahead, please, Circo first.
Luke, I mean, you have shown in the slides that actually the lowest ones, so at 21 kilometer altitude, were those with highest energy. So why is it that these gave the smallest signal in your seismic data?
Right. So, sorry, these fragmentations here.
Mm-hmm.
So these ones occurred at a low. They've occurred lower, and these ones at the end occurred much higher. And so the ones that occurred much higher had to travel through more atmosphere. And so, and so the ones that occurred higher had to travel through more atmosphere and therefore are more attenuated, and therefore the actual energy deposition from them would be much stronger than they are shown here.
Okay, interesting.
Does
I would
that
have really
answer-
expected the other way around, but that's a good explanation.
All right. Any further? Go ahead.
Yeah, thank you. Can you go back to the first slide with the yeah, that one.
This
No,
one.
no, go on, get ahead.
Oh, sorry.
Yeah. Okay.
This one.
This
Perfect.
one. If the meteoroid moves from left to the right, then I thought that event number 5 would be the first.
So what happens here is that if it arrives overhead, right, an event happening at 5, right, the meteor, the distance between, the time between the meteor going from 5 to 1 is on the order of a few seconds, whereas the timing from the acoustic wave to go from 5 to the height of 1 is on order of tens of seconds, because the timing here is controlled by how fast our meteor is traveling.
Okay, I understand. So the direction of the arrow is not real. It is much steeper. So the acoustic path is much longer from 5 to the station than the acoustic path of 1.
Absolutely, yeah. Sorry, this drawing might be a bit misleading. The actual distance between 5 and 1 in height is about 12 kilometers. So
maybe it's a little bit misleading. It should be put steeper than.
Absolutely.
Okay, thank you.
Thank you for the clarification. Any further comment, question? Someone? Tammo?
A short question. I really like the presentation, and also that you're sharing your code. You mentioned that it will be on GitHub. Where on GitHub?
It's not there yet. It's still being tested, and it produces a lot of visual user GUI bugs right now. It will be available with a paper. And the link will be in the paper when it's decided where it will be.
Public. Yeah. Okay. Good.